We'll record this for Will. So your next video, the first, I've had some problems with the video. I don't know. I'll see how it goes, but I wasn't able to get in Sunday to make the video, the first videos anyways. It never pasted. So that was a problem. Darn it. What? No. Because there's a thing, I just don't want too much information on it. So, okay, fill in the blank with the best word or phrase. Blank, who concluded? Everybody else is here. Jim ran like 10 minutes late. Well, 11. No. 11:11. Or no, maybe it is extended. Well, I know, but you got to try to get to class on time. Who concluded? Galileo Galilei? Galileo Galileo? If it were not for friction, an object in motion would keep moving forever. See this with the inclined planes and stuff. Then Newton, most of you got that one, elaborated with his first law of motion that every object in a state of rest or in a state of uniform motion, or even if you just put motion, I was all right, in a straight line at constant speed unless it is compelled to change that state by forces or net forces acting upon it. Inertia is the resistance an object has to change its state of motion. Mass is a measure of inertia. The mass of an object depends only on the number and kind of atoms in it. Mass does not depend on the location. Although I took some things like weight, because weight is based on location of the object. The weight of an object is the gravitational force acting on it. The net force, which is the resultant or total sum of all forces acting on an object, affects the object's state of motion. An object is in equilibrium when it is at rest or moving with a constant velocity with zero net force acting on it. It's not zero outside force because the outside forces just have to cancel each other out. Okay? Does that make sense? Okay. The next one shows a skier. Oops. Now he was supposed to be going downhill. Everybody seemed to get that. And so, but most of you got this okay. With FG down, the portion of FG in the plane, F parallel, FF up the hill. It said it's in equilibrium, so those should be equal. And then perpendicular F parallel. But some of you drew perpendicular straight up. It's perpendicular to the hill, 90 degrees to the hill, 90 degrees to the surface. Okay? Crazy cow sign. Where'd it go? Oh, all right. Now, the cow is not in equilibrium. Oh, why am I back in? I want to be on this, sorry. Now, some of you left off friction, which is okay. I didn't take off, did I? Oh, well, you can't put F perpendicular because that doesn't make sense. You could put friction. It's not in equilibrium, so the FG should be bigger than the FF. What? Well, sorry about that. Now here's for the car, you could have done it in a couple of ways. You could have just done this. FG and F perpendicular. That was okay. But if you wanted to put the ground and the friction of that in there, then you could have put on, F push, F friction on there like that. Well, what's pushing it forward is actually also friction, believe it or not, because the tires push into the ground pushes it forward. And then the other type of friction that would be working against it, if you were maintaining a constant velocity, which you had to because it's in equilibrium, would be air resistance, that sort of thing. So, because when I walk right now, the only reason I can walk is what? It's friction, right? I'm pushing into the ground's pushing on me. So we usually talk about friction as opposing motion, but this push force forward of the car, they crank the wheels, all the energy burns up in the engine to turn the wheels, but the wheels are pushing into the ground is pushing the car forward. That was weird. Okay. And then the tug of war, dude. There's the tug of war, guys. And I said the red-shoed boy. You can see it is red shoes now. And there would be a tension force in the rope. There would be a friction force back. Since he's not moving. Or he's at least he might be moving, but he's in equilibrium. He could be sliding in constant velocity. And then F perpendicular and FG. Right? Does that make sense? What's the problem? Why don't you just go get it and bring it over? All right, now the next one, we had this thing in it, and Spencer was working on a force board, and he had this arrangement. So you could see the weights hanging off. It was a little hard to see, but it didn't really matter. All you needed was the forces in the direction. At least I think it didn't matter. And then it said, sum the vector components, the 8.5 and the 4.9, no, 9.81. Okay, so what I did was I just made, I'll make this x, right, and that y. That makes it easy to get the components, you see, because now I know, like, this angle right here is 10, 20, 30, 40, 60 degrees. Okay, this angle here is 30. The rest goes, the other one's just going straight down. So if I call this like vector A, and this one vector B, and this vector C, now I can just find, like, for the 8.5 one and 9.8 one, I'm going to find, so if A is 8.5 newtons, I can find AX, which would be, it's negative, so minus 8.5 newtons times the cosine of 60 degrees. I just used my component methods to get this vector sum, right? And AY is positive 8.5 newtons times the sine of 60 degrees. So 8.5 cos 60 is 4.25, so that would be minus 4.25 newtons. 8.5 sine 60 is 7.36 newtons, positive. And then for the B one, it has, that's 9.8 newtons down, so Bx is 0, and By is minus 9.8 newtons. Then I could sum them. I sum to find the Rx and the Ry. And the Rx will be minus 4.25 newtons plus 0, or minus 4.25 newtons. See what I did there? And then Ry would be 7.36 newtons minus 9.8 newtons, which is minus 2.44 newtons. And then we're going to find R by Pythagorean, Rx squared plus Ry squared. And some of you found direction, which is good, but you didn't actually have to do that for credit. So the square root of that is 4.9 newtons. What do you notice? It's the third one. Now, if you didn't do this one, you should still pay attention because, you know, it may be a problem on your midterm or something. You know? So 4.9 newtons. It's the same as that one. So when we put A and B, the sum of A and B gave us a vector 4.9 newtons down like that. Then we do the next part, which was the sum the next ones, whatever they were, vector components of 8.5 and 4.9. Well, the nice thing about that so far is that we've already done the 8.5 one. We have A was 8.5, and I know AX equals minus 4.525 newtons, and AY equals plus 7.36 newtons, right? So I already have that one. That's for the 8.5. Then the other one, the blue one, was 4.9 newtons. We'll call that C. And that's at 30 degrees up here. See it? So I could do CX and CY. 4.9 newtons cosine of 30 degrees. They're both in the first quadrant, so they're both positive. Sine of 30 degrees. 4.9 cos 30. 4.24 newtons. And then 4.9 sine 30. 2.45 newtons. Okay. So when we solve the R-axis of these, we get minus 4.25 newtons plus 4.24 newtons, or basically 0 newtons, right? So we have no y, or no x, and y is 7.36 newtons plus 2.45 newtons, which equals 9.8 newtons. So that means R is 9.8 newtons. And what do you notice about that? So when we sum the 8.5 and the 4.9, we get 9.8 newtons up, equal and opposite to what? B, 9.8 newtons down. What do you think is going to happen for the next one when we sum 4.9 and 9.8? Right. So this one, for 4.9, C is 4.9 newtons. So CX, we did it already, was 4.24 newtons. And CY was 2.45 newtons. And then for BX was 0, and BY was minus 9.8. Okay, so this gives us an Rx equal to 4.24 newtons, and an Ry equal to 2.45 minus 9.8, or minus 7.35 newtons. So R would be the Pythagorean of 4.24 squared plus minus 7.35 squared. .5. fully explain between vectors, vector sums, and equilibrium. So you could say something like this. The force board is in equilibrium. So the tension of 1 plus the other is equal to the last remaining tension. Or, as an example, A plus B equals the equilibrium of C. Because it's a vector, but it's going in the opposite direction, right? So most of you didn't try that one, but some of you did try, got full points on it. So, and then some didn't do the Pythagorean part. So you found the components, and you summed the components, but you didn't find the vector sum by doing Pythagorean. So that threw you off. So now you're like, oh, right? Darn it. Well, it's a good thing if you look at it and you're frustrated because you make mistakes and you see your mistakes. It's better than like, I still don't know what he's talking about, which may be the case in some cases. But we'll keep trying. Keep going. More practice can lead to more understanding. Okay, next one. Numero dos on partato peso tres. I took 3 years of Spanish, believe it or not. It didn't sound like it, though, did it? A lot of jibber jabber. What did I say? Oh, floor 3. But I didn't know what is page 3. Oh yeah. Peggio. Peaggio. Oh, that's Italian for page. Okie dokie. So I told you it would slide down without. Well, it mattered in the direction of friction, you see, because if you didn't know, it could have slid up. But it said to draw 2 FBDs. Some of you skipped that part. So the first one, can you get this thing off? Thank you. What's the FBD on this hanging mass? FG. That's it. And then the next one, the block on the ramp, it also has an FT up. Now, because I said it would, without friction, it would slide down the ramp, that tells us that friction was in this direction. What other forces do we have on it? F perp, FG, and then the component of FG in the plane, which is F parallel. So the first thing you'll do is sum the forces for each of these in the direction you want, which is in the line of the thing here. So this one, it gives you Fg is the down equals Ft, which is the up. Whoops. Huh? Yeah. And then the second sum of the forces one is Ft plus Ff. Those are the going up the planes equal to down the planes. Then if you want to solve, you could solve for things in this second one here, because we know friction is mu F parallel, perpendicular, I'm sorry, and we know F parallel is Fg sine theta, and we know F perpendicular is Fg cos theta. So if you plug in 0.2 times 50 times cosine of 30, you'll get out 8.66 newtons. And then if you put in 50 times sine of 30, you'll get out 25 newtons. And then if you solve that for Ft, you get 16.34 newtons. Now, these problems are linked through the FTs. Okay? You always got 2 feet, don't you? But they're the same, basically. This foot is the same as that foot. Is that a useful mnemonic? I don't know. Not really. So Fg here is also equal to 16.34 newtons. Now it said calculate the mass, but some of you stopped there. Calculate the mass. You had to plug in what Fg is here. Mg equals 16.34 newtons. G is 10. Divide by 10. It's a 1.634 kilogram mass. I wonder if you went the other way with the friction, if it would come out above 5. If it would, then I didn't need to tell you the hint that I gave you in class. Well, we could easily see that. So friction was on the other side. It would be Ft was 25 plus 8, which is 33, which is still less. It would be 3.3 kilograms. So I needed to give you the hint. Not the hint. It was necessary. All right, there's a third one in this. It was pretty much just like the one on the packet, you know. So there's no excuse for you not to have full credit on this, unless you made a mistake here or there with it, because it was right on the packet. So everybody should have done this one, and everybody should have got it completely right. So, although I understand you make some mistakes. Quattro Piaggio. The first thing says draw a free body diagram. Someone give me a force. Fg. Oh, that's right. We do have an F perpendicular. That's the part that some of you forgot. even though it says it here and it gives it to you there. And then what else we got? Tension A. I'm just going to leave it A to make it a little simpler. And B, like that. And then those have with them AX, the components, AY. Yeah, I'll just BX and BY, right? Sum of the forces equals 0. Generate equations. Solve the system of equations for the unknown tensions. Well, if you do the x direction, you'll get AX equals BX. But we have to put those in component notation first. So this was 60 degrees, and this one was 30 degrees. So this will be A cos 30 degrees, and that equals B cos 60 degrees. Well, let's find out what cos 30 is. Cos 30 is 0.866. And cos 60 is 0.5. So now we have this equation. How many unknowns in that one? 2. So just this on itself, we can't do a thing. There could be a lot of A's and a lot of B's. But we could set up the sum of the forces in the y direction equals 0, which gives us I plus by. Oh, don't forget F perp equals FG. What? I is A sine 30 degrees component. Yeah. By is B sine 60. Well, you probably combined it. So plus 1,000 newtons equals 2,000. Well, some of you just did it right off the bat. You said that 1,000's coming from that and did it. That's fine. Okay. Sine 30 is 0.5. Sine 60 is 0.866. Bring over the 1,000. We have 1,000 newton. Now we have two equations and two unknowns. And we could solve like this one for A. .577. And now I would take that and plug it in. You skip the third one. Right off the packet. All right, so that goes in here. B, so instead of A, we're going to plug in B 0.577, 0.5 plus B 0.866 equals 1,000. Now that looks kind of bad, but 0.577, it's almost 12 already. This took a long time. 0.289 B plus 0.866B equals 1,000 newtons. So 0.289B plus 0.866B's gives me 1.155B's. So B equals 866 newtons. And then if we come over here, we could see and plug that in. $500. So that's just an interesting play with the sine 30 and 60 and special triangles, isn't it? And 1,000 newtons of total upward force. Yeah, that's right. Because I made a mistake. Because this was 13 out of 15. I accidentally calculated it as 15. You did them already?